In order to analyze parallel circuits mathematically, the good news is we're going to use the same exact method that we use to analyze series circuits. There are going to be some slight conceptual differences, but the overall idea of how you solve these is the same. So if I draw my table and I list however many resistors I have, and I have my resistance, my current, and my voltage column, the first step is always to list everything that you know or everything that you're given. I've decided to call this resistor R1, this resistor R2. So I've just entered in that R1 has a resistance of 3 ohms, R2 has a resistance of 8, and the total for the entire circuit, that has a voltage of 24 volts. So that's what I'm given. I filled this table out so far, and this is exactly the same procedure as when we analyzed series circuits. The next step, however, is slightly different. When I want to calculate the total resistance in the circuit for a series, I just add each number together. Parallel is a little bit different. I have to adjust something because I'm no longer going through every resistor. So since I'm not traveling through every resistor because I have different pathways, I can't just add those two together. An electron leaving this side and traveling through here will not go through the 8 ohm resistor, and likewise an electron that travels through path 2 will not go through the 3 ohm resistor. So I can't just add them together because now they're separate elements. The way we do this is we add up their inverses. So instead of adding 3 plus 11, I add 3 to the negative 1 plus 8 to the negative 1, and I will get an answer. And then I raise that answer to the negative 1. So it's kind of the exact opposite of what I did in series. Instead of adding them up, I add up the inverses and then take the inverse of that answer. So you just take the inverse each time. In your calculator, it'll be much easier to just hit 3, and there's a button that should say like x to the negative 1. So 3 to the negative 1 plus 8 to the negative 1 will give me 0.458. If I raise that to the negative 1, that will give me my total resistance. A little more complicated. Once you try this a few times and you get used to it, it'll kind of become second nature. So I now know that my resistance is 2.18 ohms, which you'll kind of notice is less than both of these. And that goes back to that concept we first spoke about. When given more pathways, you will generally have less resistance because every time you hit maybe a pathway that has a lot of traffic, so to say, you have another option. It's just like when you have toll booths and you have maybe 18 of them on the parkway and they're all next to one another, traffic can flow through there very quickly. You have lots of options. If instead they took 18 toll booths and lined them up one after the other, you can imagine how much traffic, how much slower the cars would be moving. So that's generally why you have less resistance in a parallel circuit, more options. All right, so this is the first difference we had. Now that we see we have 2 in any one row, since I have resistance and voltage for the total circuit, I can now find the total current for the circuit, which is exactly what I do using Ohm's law. If I have the voltage and I have the resistance, I can solve for current, which in this case turns out to be 11 amps. So at this point, I now have my total resistance for the circuit and the individual resistors, and I have the total current and the total voltage. Now here's where the next conceptual step comes in. We'd have to think and realize what is the same about each of these branches and what's the difference. Well, if I had 10 cars leave this side of the battery, or I'm sorry, this building, we'll say, the school, and it started to travel this way, well, if I asked you of those 10, how many went into R1 and how many went into R2, you wouldn't necessarily be able to give me that answer. The only thing you could say is, well, at any given time, there will be 10 cars split somehow between these two roads. And after these two roads or these two pathways come back together, I will have 10 cars again here. But once they're in these two, I don't necessarily know yet how many cars will go in which branch or how many electrons will go in each branch. So the way we take a look at that is to figure out what is the same. Well, if you think, if I travel through pathway 1, I pass through one resistor. If I pass through pathway 2, I pass through one resistor. And since I know that I start with 24 volts, I have to spend all of my voltage, and that I spend voltage getting through a resistor. Well, if I have to spend voltage to get through R1, and it's the only one I get through, that voltage drop must be 24 volts. Likewise, for R2, if I travel through this pathway, I pass through one resistor, I know that my voltage must drop. And if I only pass through one, start with 24, and have to end with 0, I also realize that the 24 volts must also be spent in this 8 ohm resistor. That's exactly what I've done here. Kind of explained it here, but 24 volts because you only have the one resistor you're going through. If I got to spend all my voltage and I only go through one resistor, that must be the resistor where I spend all of my voltage. So for parallel, it's generally the voltage that's the same, not the current, which is kind of the opposite of a series. Once I have the voltage and the resistance in either of these columns, now it's just a simple matter of using Ohm's law and realizing that V divided by R will give me I. So once I've done that step, I now know the resistance, the current, the voltage across each resistor, as well as for the total circuit. And now I could answer plethora of questions. Here's one quick example. I'm going to ask that you draw this circuit in your notebook. You try and figure out this table. What is the resistance, current, and voltage across each individual resistor, as well as the circuit as a whole? So if you pause the video now, I'll have the solution at the end of this video. And once you've taken a look at this and everything's fine, you can continue with today's assignment.